Welcome to lecture number 5 on matrix methods of structural analysis. Today in this lecture we will concentrate on matrix flexibility method. We will take up continuous beams today. So we are going to discuss actually continuous beams, portal frames and also redundant trusses. So today we will take up continuous beams. So today we will take a two-span continuous beam. Two-span continuous beam. Two-span. There is a concentrated force of 240 kilonewton. Beam A, B, C. The span BC carries a force of 120 kilonewton. The distance being 5 meters. 5 meters. 5 meters. 5 meters. So the fluxual rigidity of span AB and BC is uniform, both having a fluxual rigidity of EI. This is the given problem. Let us analyze the beam by matrix flexibility method. So for matrix flexibility method, the first step is finding out the degree of static indeterminacy. You know, static indeterminacy, there is more than one way of finding out the static indeterminacy. So here it is a beam of two span subjected to only vertical loading. So when there is a beam which carries only vertical loads, then the static indeterminacy equal to vertical reactions plus end moments minus 2. I'll give you the other formula for other problems. So let us take this problem with this equation. So here vertical reaction, you have one reaction. Here there will be another reaction. Here there will be another reaction. 3 vertical reactions. A being a fixed end will carry a moment. So there is one end moment, the right side there is no moment, therefore 3 vertical reactions plus 1 end moment at the left minus 2 as I told in the earlier class. So there are 3 equations of equilibrium: sigma V equal to 0, sigma H equal to 0, sigma M equal to 0. Now in the absence of any inclined or horizontal force, this equation will be of no use. Therefore, only 2 equations will be useful. So that is equal to 2. So the degree of static indeterminacy of the structure is 2. So after finding out the degree of static indeterminacy, we have to find out the primary structure. So primary structure, again we can make it as a cantilever by removing the support at B and C. It will be a cantilever. Normally the moment is the important quantity in the case of continuous beams, portal frames, etc. Therefore, we will treat MA and MB as redundant by introducing hinges at here. This is the given structure. The given structure will be made as a primary structure by introducing 2 hinges. At A and B. Therefore, we can mark it as clockwise or anti-clockwise. Say this is one redundant. This is F0. Number will fix later. So this is internal moment. So this is again F0. Number we will fix later. So that is, So by the redundants are MA, and we are introducing hinge here. So that is MA, that is one redundant force, and here MB is also removed by means of introducing a hinge in the structure. So MA and MB are the redundants. So in the force vector, this will be some F1 star, F2 star, like that. That will discuss little later. So MA and MB are the redundants. After that, we have to find out the fixed. So this is the primary structure actually. This is the primary. This structure is statically determinate because AB can be analyzed as a simply support beam and BC can be analyzed as a simply support beam. So that is a primary structure. Now we have to find out the fixed end moments. Fixed end moments. Fixed end moments MAB, M of AB equal to minus WL by 8 equal to minus 240 into 10 by 8 equal to, so 300 kilonewton meter. M of VA is equal to plus WL by 8, that is also 240 into 10 by 8 equal to 300 kilonewton meter. M of BC, treating BC as a fixed beam, M of BC equal to again minus WL by 8 because that is also subjected to central concentrated load. Therefore, this is 120 into 10 WL by 8. This is equal to minus 150 kilonewton meter, and MF CB equal to plus WL by 8 is equal to 150 kilonewton meter. These are the fixed end moments. So here it is first one is minus, this is minus, so anti-clockwise 300 kilonewton meter. So here it is 300 kilonewton meter. This is 150 meter, again 150 kilonewton meter. These are the fixed end moments. So next is the equivalent joint loads. So equivalent joint load will be, that is FE. FE will be, so here this is anti-clockwise 300. Therefore, this is clockwise 300. This is clockwise. Therefore, this is anti-clockwise. So this is minus 150. Therefore, this is plus 150, and this is minus 150. These are the equivalent joint forces. So later we'll write the FE vector. The equivalent forces will be plus 300. Minus 300 plus 150 minus 150. In the last step we will write this. Anyway, just to make things clear, I'm just writing here. This will write it at the end of the problem. So that is about the equivalent joint force. F equivalent. Now we have to form the system forces. System forces will be resulting from the application of the external forces. So this will give you the F star values. F star values are the system forces resulting from the external forces. So A, in the given problem, A is a fixed end. Therefore, that will carry the moment, that will not transfer the moment to the span. Therefore, that will take the moment. So we need not bother about this because in the given problem, it is a fixed end. Now coming to this, these two forces at B, that is 300 clockwise and minus 150 anti-clockwise, will give minus 150. So this value is equal to F1 star. So that is F1 star. Coming to the support C here, there is a clockwise moment. In the given beam, it is a simply supported end that cannot take any moment. So we have got these moments by assuming BC as a fixed beam. No, it is not a fixed beam. Therefore, you have to apply a force of 150 kilonewton meter, that is equal to F2 star, F2 star, F1 star and F2 star. That is about the system forces. These are the forces resulting from the given external forces. Next, we have to find out the element coordinates. We have to find out the element coordinates. Element coordinates, this is 1. As we discussed, we have to mark all the coordinates in the clockwise direction, 3 and 4. 3 and 4. These are we have divided the beam into two elements. So this element number 1, element number 2, divided the beam into two elements. So we have taken only the moment coordinates. So 1, 2, 3, 4 are the element coordinates. Now, the redundance. Now already we have fixed F1 star and F2 star. We have one force here redundant, F3 naught, and this is F4 naught. So this is F4 naught. This is F4 naught. This is F3 naught. F3 naught, you can mark it in the clockwise direction or anti-clockwise, no problem. So that is about the values of F3 naught and F4 naught. So after determining the system forces, element coordinates, redundant forces, etc., next thing is formation of the B matrix. Formation of the B matrix. B matrix. B matrix, what you are doing is, we have to apply, again we are going to apply the principle of superposition of forces. What we are doing is, we have to apply F1 star equal to unity, find out the values of the forces, F1 star equal to unity, find out the value of the forces along the element coordinates 1, 2, 3 and 4. Next step, apply F2 star alone, find out the second column. Like that we have to, but we will just do the problem. So for getting the first column of the B matrix, we have to apply unit force along F1 star. So this is these are the elements. This is F1 star. F1 star is here. This is F1 star equal to unity. We have to apply unit force one at a time. Now we have treated this as hinged. Actually, this is hinged here. This is hinged here. Here also it is hinged. Here also it is hinged. Therefore, when we apply unit force here, at this end the moment will be 0, and this is a hinge here. Therefore, here also it is 0. It will not be carried over. We are applying in the span BC because the need is here only. Here it is 300. Here it is 150. So minus 150 will be applied at the point B in the span BC. Therefore, F1 star is applied in the span BC, and here also it is 0. So, first column, we have to write in the same order along the element coordinates 1, 2, 3 and 4. So, at 1 it is 0, 1 it is 0, 2 it is 0, 3 it is minus 1 because it is anti-clockwise. We take the value in the same direction, 1 and 0. Of course, in some of the books this will be applied in the clockwise direction. This will be plus 1, so that need not be confused. All will lead to the same answer if the calculation is correct. So this is by applying F1 star equal to unity. Apply F2 star equal to unity. F2 star equal to F2 star is this one. So this is these are the elements. Apply in the same direction equal to 1. This is equal to F2 star equal to unity. So when you apply F2 star equal to unity, this being a hinge, here it will be 0 and here it will be 0, here also it will be 0. Therefore the second column will be in the same order 1, 2, 3 and 4. So 0, 0, 0, minus 1. This is so these are the system forces. So this matrix is called the star matrix, or you can say B star matrix. Next, we have to apply the redundance. We have got only two system forces. Coming to redundant forces, we have got F3 naught. So for getting third column, we apply F3 naught equal to unity. That is in the clockwise direction we have assumed. Yes, clockwise direction we have assumed. This is 1. This is F3 naught equal to unity. So as we have discussed earlier, this will become 0. This will become 0 because B and C are hinges. Therefore, that is the value. So this will be in the same order. 1, 0, 0, 0 is the third column of the B matrix, transformation matrix. Then F4 naught. So for getting the fourth column, you apply F4 naught equal to unity. So since that is an intermediate hinge, you applied this as 1, this as 1. This being hinged, it will become 0. Here also this is hinged. We have taken the primary structure with the hinge, so this will also become 0. Therefore, it is in the same order. 0, minus 1. Here it is marked clockwise. Here we have marked the moment anti-clockwise. So minus 1 plus 1 is 0. Minus 1. So 0, minus 1, 1 and 0. So this matrix is the naught matrix. B star and B naught. We will provide a partition here. We will provide a partition at this. So this is the B matrix. It is a very important matrix in all problems. If this is correctly derived, other things are only application of formulas and systematic calculation. It's a very important matrix. That is about the D matrix. Now, after getting the B matrix, we have to go for the element flexibility matrix. Element flexibility matrix alpha 1 for element number 1 will be L by 6EI. For element number 1 it is L1 by 6E1 I1. 2 minus 1 2. This already we have derived. This you have to apply for span 1. So L1 equal to 10 meters by 6. EI is uniform. Suppose EI is given as 2 EI or 3 EI, that you have to incorporate here. Here EI is uniform throughout, therefore 6 EI 2, minus 1, minus 1, 2. Now coming to this is alpha 1, alpha 1. Now coming to this problem, second span is also of 10 meters. That also has got EI. Therefore, the L1, L2, E1, E2, I1, I2 being the same, this is also equal to alpha 2. Alpha 1, alpha 2. Now, we have to form the assembled element flexibility matrix will be alpha 1, alpha 2, 0 and 0. Now, alpha 1 is equal to alpha 2, 10 by 6a is common. So what we can do is, we can take the assembled element flexibility matrix alpha equal to 10 by 6ei, 10 by 6ei. For alpha 1, it is 2, minus 1, minus 1, 2. Then alpha 2, third column, 2, minus 1, minus 1, 2. Along the leading diagonal, you have to mark alpha 1, alpha 2, alpha 3 up to alpha n. So this is the assembled element flexibility matrix. Assembled element flexibility matrix. So these are the values. Now, after getting the assembled element flexibility matrix, we can straight away find out the redundant forces. So there is a small correction. So this is 2. 2 minus 1 minus 1 2. So now we can straight away find out the redundant forces. You can straight away find out the redundant forces. Redundant forces F naught equal to minus of A naught inverse A naught star into F star. This is the formula already we have discussed. So A naught equal to we have discussed the formula B transpose alpha into B is the formula. This is A naught, therefore this is B naught. Second one is also naught, therefore this is also naught. B naught transpose alpha into B naught. Now here B naught star matrix, so this is the B naught matrix. So here this is B star matrix, this is B naught matrix. By applying F1 star, F2 star, we obtain the two columns. By applying F3 naught equal to unity and F4 naught equal to unity, we got the third and fourth column. So we have to make use of the second one. So B naught transpose will be 1 0 0 1 0 0 0, then 0 minus 1 1 0 0 minus 1 1. So this is B naught. B naught into alpha. Alpha equal to 10 by 6 EI, 10 by 6 EI, 2 minus 1 0 0 minus 1 2 0 0 0 0 2 minus 1 0 0 minus 1 2. This is the alpha matrix, and again B naught into B naught is equal to into B naught equal to 1 0 0 0 0 minus 1 1 0 minus 1 0. Now here, at least for one step, you have to explain the procedure. Matrix multiplication is fundamental only. Still, for the benefit of the viewers, I will just explain the calculation procedure. When we multiply first and the second one, first one and the second one, so you will get 10 by 6 EI equal to 10 by 6 EI. 6 EI. First one, first row, first column. First row, 1 into 2, 1 into 2 plus 0 into 0 plus 0 into 0, 0 into 0. So plus 0 equal to 2. So first row, first column will give you the first value. Sorry, 2. It is 2. Then first row, second column. First row, second column is 1 into minus 1, that is minus 1. Then 0 into 2, 0, 0, 0, 0. Therefore, this value will be first row, second column. That is, the first row, second value will be minus 1. Minus 1. Then first row, third column. First row, third column, this is 1, this is 1. Third column is 0, therefore 1 into 0. All other values are zeros, therefore that will be 0, 2, 1, 0. Similarly, first row, fourth column will also be 0. First row and fourth column. Fourth column, here it is 1, all other values are 0. So here it is 0. So first value becomes 0, all other values. So that will also become 0. But that is first row, first column, first row, second column, etc. One more calculation, and later I will write the matrix straight away. Second row into first column. Second row, 0 into 2, 0. Minus 1 into minus 1, plus 1. This into 0, this into 0. So therefore, minus 1 into minus 1 will become plus 1. This is the second row, first column. Second row, first column. Similarly, when you do the calculations, because I don't have the values, anyway, we'll just write. I will 0 into minus 1, minus 2. This is minus 2, minus 2, 0, 1 into 2, 2. This is 2, first row, second row, fourth column, 1 into minus 1, which is minus 1, minus 1. So this is, so first row, all these columns, second row, all these columns, that will give you, so this is actually, this consists of 2 rows and 4 columns. This is of size 4 by 4. So when you multiply these two, you will be getting a matrix 2 by 4, 2 rows and 4 columns. So this is after multiplying the first two. Now again it is to multiply by this. So this into this will be 1 0 0 0, 1 0 0 0, and then 0 minus 1, 0 minus 1, 1 0. So same line, first row, first column, one value. First row, second column, second value is equal to 10 by 6 EI into first row, first column will be 2. First row, second column will be 1. Second row, first column will be 1. And this is equal to 4. This is the A naught naught matrix. This matrix is the A naught naught matrix. This is what A naught naught we have calculated. A naught naught. As per the formula for the redundant forces, we have to find out A naught naught inverse. A naught naught inverse will be, so inverse will be, this will become 6EI by 10. This will become 6EI by 10 into 1 by determinant into adjoint of the matrix. 1 by determinant will be 2 into 4, 8 minus 1. 1 by determinant will be 8 minus 1 into adjoint of the matrix. Adjoint 2, 4 will get interchanged. So 4 will come here, 2 will go here, and the other values will be minus 1, minus 1. This is the A naught naught inverse matrix. So A naught naught inverse matrix. So A naught naught inverse. A naught naught inverse. So one step is over. Next, A naught star. A naught star equal to, A naught star is equal to, we know the formula is B transpose alpha into B. That is, here it is A naught, therefore it is B naught. Here it is star, therefore this will be B star. B star. So B naught transpose as before 1 0 0 0 1 0 0 0 0 minus 1 0 minus 1 1 0 1 0 into alpha 4 by 4, that is 10 by 6EI into the 4 by 4 matrix. 4 by 4, I don't want to repeat. 4 by 4 this matrix you have to rewrite. Then coming to the third one, B star. B star is 0 0 minus 1 0. B star into 0 0 minus 1 0 and 0 0 0 0 0 0 minus 1. So this again, this is 2 by 4, 2 rows 4 columns. This is 4 by 4. So multiplying these two, you will get the 2 by 4 as before. Then 2 by 4 into, this is 2 by 4 into, this is 4 by 2. 4 rows 2 columns. 4 rows 2 columns. So 4 by 2. So this, on multiplying this and this, we will be getting a 2 by 2 matrix. So again, I don't want to spend time on multiplying because already I explained how to multiply matrices. Therefore, that will directly give you the A naught star matrix. So multiplying these things, we will get A naught star is equal to, A naught star equal to 10 by 6EI. After multiplying, you will be getting 0 0 0 0 minus 2 1. That is the A naught star matrix. We know the redundant forces. Redundant forces F naught equal to minus A naught naught inverse A naught star into F star. Now, F star already we have calculated. F star consists of F star equal to F1 star and F2 star. F1 star is 150. F1 star equal to 150. F2 star is also 150. Here one point is to be observed. That is, here we are writing F1 star and this is anti-clockwise. This is also anti-clockwise. but we are writing with the plus sign. The reason being, when we have derived the B matrix, we have taken F1 star in the same direction. In the elements, we have taken F1 star is in the anti-clockwise direction only. Therefore, again you should not F1 star, yes, this one, minus 1. Similarly, when we have considered F2 star also, this is applied in the anti-clockwise direction. Same direction we applied. F1 star equal to unity, F2 star equal to unity, we have applied in the anti-clockwise direction itself. That is why we are getting minus 1, minus 1. Therefore, again, because it is anti-clockwise, you should not put minus here. In some other textbooks, this is marked anti-clockwise. When we do the calculation, this is marked in the clockwise direction, this is also marked in the clockwise direction. If these values are marked in the clockwise direction, then we have to write minus 150, minus 150. This is a very important point. Minus 150, minus 150. Here, there is no such need. Therefore, we write with a plus sign. Therefore, redundant force is equal to, that is a point to be remembered. Otherwise, the values will go wrong. Now, minus A naught naught inverse. Minus A naught naught inverse is 6EI by 10. Minus 6EI by 10. Here it is, yes, A naught naught inverse is equal to, this we are not finalized, we are not, this is equal to actually 6EI by 10. I'll write it here for want of space. A naught naught inverse is equal to 6EI by 10. 6EI. This is 10. 8 minus 1, 7. So we will write it as 6EI by 70. 6EI by 70. Then 4 minus 1. Minus 1, 2. 4 minus 1, minus 1, 2. That is the value of A naught naught inverse. Therefore, this is 6EI by 70 minus 6EI by 70. 4 minus 1. 4 minus 1 minus 1 or 2. This is A naught naught inverse into A naught star. A naught star is 10 by 6EI. 10 by 6EI. 6EI. 0, 0, minus 2, 1, minus 2. So this is A naught star into F star. F star is 150, 150. 150, 150. So this is the equation for the final force. So this is actually 2 by 2. So this 6EI will get cancelled, and this will give 7. So that is a number. So 2 by 2, this is 2 by 2. This is also 2 by 2. The third one is 2 rows and 1 column, 2 by 1. So multiplying these two are 2 by 2. Multiplying these two, you will be getting a 2 by 1. That is as before. First row, first column. First row is 4 into 0, minus 1 into minus 2, that will be 2. First row, second column. Then second row, first column, second row, second column. That will give you the product of these two. Then again you have to multiply this. So first, second, then multiply by 3. You will be getting a 2 by 1 value. The 2 by 1 value will be 2 rows, and after multiplying everything, you will get F naught equal to, you will get the multiplication of this will give you F naught equal to minus 21.43, then 42.86. These are the redundant forces. So this you have to get it. So that is the value of the redundant forces. Redundant force is equal to F3 naught equal to minus 21.43, F4 naught equal to 42.86. That is about the redundant forces. So this is your F3 naught, this is your F4 naught. And therefore now the force vector F equal to F star, F naught, F star and F naught equal to 150, F1 star, F2 star, F3 naught equal to minus 21.43, this is 42.86. So this is the force vector, including the system forces and the redundant forces. So that is the force vector. Now from this force vector we have to get the element forces P. We know element forces, we use F for system forces, P for element forces. Already we have discussed P equal to B into F. So B matrix actually is 0 0 0 0 minus 1 0 0 0 0 minus 1 1 0 0 0 then 0 minus 1 1 0. This is the B matrix that we have already derived. Multiplied by F. F is equal to this value, namely 150 minus 21.43, 42.86. So this is the value. Now when we multiply these two, we will get first row, first column. First row 0 into 150, forget about it. 0 into 150, forget about it. Then 1 into 21.43, minus 21.43. So first value will be minus 21.43. That is 21.43. Second, 0 into 150, 0 into 150, 0 into 21.43, minus 1 into 42.86. Therefore, this is minus 42.86. Like this, if you complete, this is minus 107.14. 107.14. This is minus 150. This is your element forces. After getting the element forces, the final force P, F equal to P minus P equivalent, or you can write P plus P dash. P plus the fixed end moments, or P minus the equivalent joint force. So P is equal to this value, namely 150. Not this value. 21.43 minus 21.43 minus 42.86 minus 107.14 minus 150. This is P minus P equivalent. P equivalent, actually the fixed end moment was anti-clockwise. PE is equal to clockwise 300. Already we have done it. 300. This is 150. These are the equivalent joint forces. Already we have marked in the figure. Therefore, that will be 300 plus 300 minus 300, 150 minus 150. Or what we can do is we can use a plus sign and write the fixed end moment, because we know fixed end moment the left hand is minus 300, so you can use plus sign. That also can be done. So the sum of these two will give minus 321.43, that is equal to sum of this equal to minus 321.43 minus 300, this is plus something, therefore 257.14, because this is minus and minus is plus 300 minus 42 something. This is minus 107, this is minus 150, this is also equal to minus 257.14. Now this is minus 150, this is minus into minus plus 150, therefore this value will be 0. These are the final moments. So for this final moments, we have to draw the bending moment. So that is about getting the final moments. To draw the bending moment diagram, what we have to do is, this is AB, this is BC, the final moments here is minus, therefore anti-clockwise 321.43, this is clockwise 257.14, this is third one minus 257.14, and here it is 0. So this is the beam, this is the beam. So this will cause tension at the top. So mark it here at the top, 321. So these two also will cause tension at the top. Tension at the top. That is also 257.14, and here it is 0. Here it is 0. Therefore, this is the support moment diagram. This is 321.43 kilonewton meter. This value is equal to 257.14 kilonewton meter. Now first span is subjected to the central load. You have to find out the simply supported moment. Mu AB equal to WL by 4. Bending moment for a simply supported beam subjected to central concentrated load equal to 240 into 10 by 4. 240 means 60 into 10 equal to 600 kilonewton meter. Mu BC equal to bending moment as a simply support beam, WL by 4, W equal to 120 into 10 by 4, that is 300 kilonewton meter. Therefore, so for this, the simply support beam is a triangle having a maximum ordinate of 600. This value equal to 600 kilonewton meter. This value equal to 300 kilonewton meter. Now this is minus, this is plus, this is minus, this is plus. This is the net bending moment diagram. This is the bending. Final bending moment diagram. So this completes one full example on a continuous beam by matrix flexibility method. We will take other examples in the next class. Thank you all. Thank you.